The materials that built the industrial age still reward those who understand them. By the late 19th century, the modern world was being forged not just by steam and steel, but by an intimate knowledge of raw materials. Craftsmen did not rely on digital calipers or automated polishers. Instead, they relied on metallurgy, patience, and chemistry. If you want to understand how field instruments, precision tools, and reflective devices were built in the 1880s, and why many still survive today, you must start with the materials themselves. This is not nostalgia. It is technical literacy rooted in history. When you understand the base alloys, the abrasives, and the slurry chemistry, you begin to see how 19th century craftsmen achieved durability and optical precision without electricity. The base metal alloys of the 1880s were engineered for weight and endurance. The backbone of many field instruments in the 1880s was brass, particularly high-quality cartridge brass, composed primarily of copper and zinc. The common formulation hovered around 70% copper and 30% zinc. This ratio provided a balance between malleability and structural strength. It resisted corrosion in damp environments and held threads cleanly for screws and fittings. For components that required additional strength, small amounts of tin were sometimes introduced, creating bronze variants with improved hardness and wear resistance. Weight was not an inconvenience. It was a stabilizing force. Surveying instruments, signal lamps, and optical housings required mass to dampen vibration. A heavier alloy meant steadier performance in the field. Modern lightweight alloys often sacrifice this mechanical stability. In contrast, Victorian engineers prioritized durability over portability, particularly for military and maritime applications. If you were to apply this knowledge today in restoration or replica work, start by selecting brass stock that mirrors historical ratios. Avoid modern decorative brass that prioritizes shine over structural integrity. Machine it slowly, respecting its work-hardening characteristics. Brass hardens as it is shaped, so periodic annealing with controlled heating restores its malleability. This was standard practice in 19th century workshops. The transition from power tools to authentic abrasives, well, it really does reveal true craftsmanship. Modern workshops, they depend on electric grinders and diamond-coated discs. But Victorian craftsmen, they relied on abrasives derived from natural minerals. Emery, which is a granular form of corundum mixed with iron oxide, was actually one of the most common. It provided a controlled cutting action that was just right for metal shaping. Pumice and rottenstone, on the other hand, were used for the finer finishing stages, especially on softer metals and wood. These powders were applied using wooden laps, often hand-carved from hardwoods such as beech or boxwood. The wood served as a carrier for abrasive particles, conforming slightly to the workpiece and distributing pressure evenly. The lap was charged with abrasive and worked manually in circular or figure-8 motions. This method helped reduce heat build-up and preserve the surface geometry. To apply this in practice, you'd begin with a coarse emery powder mixed lightly with oil for the initial smoothing. Then you'd progress gradually to finer grades. It's important to replace the lap surface when it becomes contaminated with larger particles, since cross-contamination can introduce scratches. Patience really defines the process. The absence of electricity forces attention to detail. The chemistry of the slurry, Well, that's what determines optical precision. Creating a reflective surface capable of projecting a tight, controlled beam requires more than simply polishing until something shines. The slurry used in the final polishing stages determines the surface microstructure. For brass reflectors or optical housings, Victorian craftsmen often used jeweller's rouge, which is primarily iron oxide in a very fine, particulate form. When mixed with a light oil or distilled water, it forms a polishing slurry that removes microscopic peaks without gouging the surface. The chemistry matters because particle size controls abrasion rate. Larger particles cut aggressively but, of course, leave scratches. Submicron particles refine the surface to near-mirror quality. The slurry must remain evenly suspended, so it should be stirred frequently. Too much oil reduces cutting efficiency, while too much water evaporates quickly and can cause uneven drying marks. For tighter beam reflection, surface smoothness must approach optical standards. After initial smoothing with fine emery, you'd transition to rouge slurry, applied with a clean wooden lap or felt pad. Work slowly and inspect under direct light. The goal is uniform reflection without distortion. Uneven polishing introduces scatter, widening the beam and reducing intensity. If restoring a historical reflector, it's best to clean oxidation first with a mild acidic solution, such as diluted vinegar, then neutralize and dry thoroughly before polishing. Always test on a small section to avoid removing excessive material. 19th century craftsmen, they really valued restraint. Removing too much metal compromised structural integrity. Why does 19th century material knowledge still matter today? Well, understanding these raw materials provides more than just historical trivia. It reveals how durability and precision were achieved without synthetic compounds or automated systems. Brass alloys were chosen for predictable behavior. Abrasive powders were graded and applied in deliberate stages. Slurry chemistry was controlled through careful observation rather than digital measurement. For survivalists and restoration enthusiasts, these principles offer independence from modern supply chains. If electricity fails, hand tools and mineral abrasives still function. If industrial polish isn't available, iron oxide powder remains effective. Mastery of materials reduces dependence on infrastructure. For history enthusiasts, this knowledge deepens appreciation for Victorian engineering. These were not crude approximations. They were carefully calibrated processes developed through experimentation and experience. Mastery of materials is, in fact, mastery of the outcome. The 19th century reminds us that craftsmanship begins with understanding raw materials. Brass ratios determine strength. Abrasive selection shapes surfaces. Slurry chemistry defines reflectivity. Each decision really influences performance in the field. When you study these processes, you recognize that innovation didn't begin with microchips. It began with metallurgy and chemistry, applied patiently by skilled hands. That is a lesson, I think, well worth preserving.